in this next chapter, we are back to talking about things in solution. This time we are talking about when something is fully dissolved in its solvent and how having those particles in solution affects the properties of the solution. So we'll start with just some definitions, most of which are probably reminders at this point, but just to make sure that we have them all down. So when we talk about solutions, by definition, we're talking about a homogeneous mixture of two or more substances and the solvent is whatever thing is present in the majority, so it's the majority component. And the solute is the minority component. Now, for a lot of what we talk about, the solute ends up being some type of salt, like sodium chloride, that we then dissolve in some liquid solvent. But we will, by the end of this chapter, move to talking about binary liquid mixtures. So in that case, both things that we're mixing together are going to be liquids, and even the majority-minority designation may not be quite right because it's possible to have a perfect 50-50 mixture. But until we get to that, solvent is the thing that's present in the majority, solute is in the minority. And if we have an aqueous solution, it just means that the solvent is water. All right, so something about solutions, which I'm going to abbreviate a little bit here. Solutions undergo something called spontaneous mixing. And what this means is that if the solute is soluble, it will mix with the solvent automatically. To become a homogeneous mixture. So by soluble, I'm going to underline soluble here. So solubility, just like with every other time we have talked about solubility, the solubility rules are just the beginning. So when we talk about insoluble things, the solubility rules tell us that something is insoluble, but then we applied equilibrium on top of this concept to talk about degrees of solubility for insoluble things. Now we're talking about degrees of solubility for soluble things. So for solubility, we can also talk about this as the amount of a substance that will dissolve in a given solvent. So an example of this, sodium chloride, at 25 degrees C, you can get 36 grams dissolved per 100 grams of water. So that's pretty soluble. All right, So the thing that is driving this spontaneous mixing in most cases, sometimes we get a little bit of help from some other areas, but mixing in solution occurs to increase entropy. All right, so if we have already talked about thermodynamics, this probably makes some sense. If for some reason you're looking at this before we do thermodynamics, entropy is a measure of disorder. So essentially, there's a law in thermodynamics that tells us that reactions like to proceed in the direction that increases the entropy of the universe. So if we can take a solute and split it up and mix it up with a bunch of solvent molecules, that would increase the entropy, which is a good thing in terms of getting things to mix together. All right. So built on top of this and the intermolecular forces that we talked about in a previous section, we can look at different, we'll say types of compounds and ask the question, is it miscible? And this depends on intermolecular forces. This is the basis for a rule that you might have heard before, which is that like dissolves like. Which is essentially if you have a polar or an ionic solute, it will dissolve in a polar solvent. If you have a nonpolar solute, it will dissolve in a nonpolar solvent. So let's say nonpolar solutes dissolve in nonpolar solvents. Polar or ionic solutes dissolve in polar solvents. So the last thing that I want to talk about in this video are units for concentration. So describing solution concentration. We have used some of these units before. We will use more of them in this chapter. And you will also see these definitions on the equation sheet. So what I'm going to do, I'm going to give you these definitions, and then there will be practice problems and homework problems where you will be asked to practice with them. Practicing with them is going to be the biggest help in terms of being able to use the units. Plus, you'll see them applied in some of the problems as we go through the rest of this section. So, one that you have seen before is molarity. So remember, we use a capital M for molarity, and this is moles of solute over liters of solution. So this is why when you are in the lab and you're making these solutions of specific molarities, you are dissolving all of your solute in a little bit of solution and then adding the rest because you're looking for the total volume of the solution, including the solute. All right. Another concentration unit is molality. And so we use this lowercase, I don't know, like cursive, I just call it lowercase fancy m, for the symbol for molality. And molality is moles of solute divided by kilograms of solvent. So here's the thing. I think that molality has a really bad reputation and people tend not to like it. But molality is one of the best concentration units you can use because the solute and the solvent are separate. And because we're using a mass of solvent, this concentration unit doesn't depend on temperature. So you may have seen in other examples where something like water has a different density at different temperatures. Well, that will affect your molarity of solution. And the glassware that you use in lab is only rated for specific temperatures technically. But if we calculate a molality, your molality is the same across an entire temperature range. I guess as long as you don't accidentally freeze or boil your solvent, you're pretty good. So molality we will use quite a bit when we start talking about properties of solutions. Mole fraction is one that we have seen before. So we use a chi for this, and it is moles of solute over total moles. So remember, this is solute plus solvent. And from the mole fraction, you can calculate a mole percent if you just take your mole fraction and multiply it by 100 to give you a percentage, because the mole fraction is going to come out as a decimal. And the last three, so everything that we have done so far has been by moles. We have a set that we can do by mass. So we've done something like mass percent before. So mass percent, we did mass of solute over mass of solution. And then if you take this and multiply by 100, you get a mass percent. Now this also works for two other types of units. If instead of multiplying by 100, you multiply by 10 to the 6th, you get something called ppm, which is parts per million. So this is really great for something that's not super concentrated. And if we do times 10 to the 9th, you get something called ppb, which is parts per billion. So you will see a lot of things like pollution measured in parts per million or parts per billion, because we're looking at hopefully very low concentrations of something in solution, and we tend to talk about air as the solvent in this case.